Hi, I'm Norman Jouppi, and I work at the Digital Equipment Corporation's Western Research Lab. And I'll be speaking today about high-performance, high-power ECL microprocessor. You can see on the first slide I have quite a number of co-authors, and this may look like a lot of people, but in reality it's all the people involved in the chip design, large CAD effort, packaging of the high-power microprocessor, board-level design, and our lab director. So in reality, there's not many people working on each aspect. The chip is a 300 megahertz, 115 watt, 32-bit bipolar ECL microprocessor. And one number you should pay attention to is the third number, and it's a 32-bit microprocessor. There has been a little confusion. Some people might be confused and think that this is an alpha. But an alpha is a 64-bit architecture, and this is a 32-bit architecture, so it's not an alpha. What is it? Well, it's a subset of the MIPS R6000 architecture. The chip was designed a number of years ago, before alpha came out, basically. The subset includes all the integer functions except for integer multiply and divide, but does not include any floating point or memory management support. Okay. This chip was the result of a research project which had a number of interrelated goals. First, what we wanted to do was develop expertise in custom ECL design, microprocessor design specifically. And a little background on this, primarily other than communication circuits, ECL has been used for large gate array multi-chip module mainframes. And the density of the gate arrays is not very good, and because it's a very large machine, many chips, multi-chip modules, it's very expensive. Also, we all know that you suffer quite a bit of performance from having a gate array over a full custom design. So we wanted to see what kind of performance we could get with full custom ECL, as opposed to the gate array ECL, which is so common in the industry. In order to do that, we needed some enabling technologies. First, because we achieved much better density with the custom ECL than with the gate array design. We had higher power density. Although we had higher power density, we just had one chip. So there was many different packaging trade-offs than the conventional lower power per chip, multi-chip module kind of environment. So we had to develop high-performance microprocessor packaging, both thermal aspects and electrical aspects of the package. Finally, in order to do the design with a small number of people, we need to develop CAD tools for synthesis of the layout and analysis of VLSI ECL circuits. Those kinds of CAD tools obviously aren't available in the industry. In order to keep the work manageable, we had a number of non-goals. Those non-goals included implementing of the floating point of virtual memory, which I talked about before, and multi-processor support. Obviously, if we didn't have a complete processor, it did make sense to support multiple processors. And because we didn't have a floating point and other things needed for running large benchmarks, obviously the highest spec mark was not one of the major goals of the project. Okay. Here's a number of the technical details on the project. We used a 1-micron single poly bipolar process, and bipolar can come in double poly or single poly forms. This is the simpler form. And the lithographic feature sizes that we used were only 1 micron. So it's not very aggressive in comparison to most of the other chips that you'll be hearing about typically in CMOS are around 0.6 or 0.8 micron these days. But we had quite a number of devices considering the lithography. We had 2/3 of a million devices, of which about 500,000 were bipolar transistors. We had 2 power supplies. The main power supply for all the circuits internal to the chip was a -5.2 volt supply. ECL uses a negative supply with the higher supply rail being ground. And we had a 21 amp supply current. So to put things in perspective, a standard wall outlet is only 15 amps, and so this is a fairly high supply current, albeit at a lower supply voltage than a wall outlet. So that was an interesting area of research. We'll see some results later. We also had an input termination supply of -2 volts, which worst case would draw 5 amps, but usually drew less. In order to run the processor at a higher clock frequency than the external board, which was one of our major goals, we needed on-chip instruction and data caches. So we had on-chip 2K byte data and instruction caches. These were lower density than you might find in a BiCMOS design, by about 4 times less density, because we didn't have BiCMOS capability in this design. We used a 504-pin package, of which 366 pins were used for signals and the rest for power and ground. We were able to run the on-chip clock at 300 megahertz, and we dissipated 115 watts of power. So in order to put 115 watts in perspective, what I've done is I summed up all of the power of the previous the chips at last year's Hot Chips conference, and you can see we come up with 73 watts. And for one thing, that's only a 2-digit number, and it's much smaller than our 115 watts in our single chip. Now, I wasn't able to add in powers for 9 chips. They didn't list their power, and I find that surprising. You'd think at a Hot Chips conference people would want to list their power dissipation. But okay. One point I want to make, though, is that high power dissipation does not mean necessarily high temperature. Here's a numerical model of the die temperature, and we can see the dark areas in the center of the chip are the highest temperature, and that's about 94 degrees centigrade. The lowest temperature is in the lower right-hand corner, and that's basically where we don't have any active circuitry, so that doesn't dissipate much power. But you can see that the die temperatures less than 100 degrees centigrade maximum are actually typical of that found for CMOS chips in plastic packages, and they're not unusual chip temperatures. I'll explain a little bit more about the actual layout of the die later when I see a chip floor plan. Okay. This slide here shows how we achieve those low temperatures with our high power dissipation. What we used was a thermosiphon. And a thermosiphon is basically a heat pipe without a wick, for those of you who know about heat pipes. You'll see in the slide that the die is bonded directly to a boiler instead of bonding it to the package first and then bolting on a heat sink. So this eliminates thermal interfaces and reduces the thermal resistance. The boiler is in contact with the main part of the thermosiphon, which is a condenser, and it's filled with a working fluid, in our case alcohol-water mixture. The boiler boils the fluid, and the vapors rise and condense on the sidewall of the tube, and then trickle back down. Now we keep the alcohol-water mixture at subatmospheric pressure to lower the boiling point and achieve a lower die temperature. In order to cool the condenser, we use just normal workstation kind of airflows, quiet, low-velocity air. Now, one thing that's important to point out is because it's a thermosiphon and not a heat pipe, the difference between those is a heat pipe has a wick, a thermosiphon does not. The thermosiphon needs to operate in a kind of vertical orientation. If you turn the thermosiphon upside down, you can see the fluid would be on the other end of the condenser and wouldn't be in contact with the boiling surface, and this wouldn't be a good idea. But actually, if you operate the thermosiphon somewhat tilted, say at a 45-degree angle, it actually operates better because the liquids can come down on one side and the vapors go up on the other, and they don't interfere with each other. Whereas if you operate it vertically, bubbles of vapor can get in the way of returning fluid. And the thermosiphon actually operates all the way down to about 80 degrees on either side fairly well. Here's a photo of the package. that we used. And you can see that the plastic pin grid array is about 2.5 inches on a side, and we have a fairly short Thermos siphon. It's only 2 inches tall. We also have Thermos siphons that have higher condensers. Here's an example here of pretty much a standard version. It's about twice as tall as the one in the photo, and this just gives us a lower thermal resistance term on the condenser side. So there's a number of electrical points that I want to make about the package. First is that by using a plastic pin grid array instead of ceramic, we were able to achieve much better electrical characteristics. The plastic pin grid array is made out of similar materials of a PC board, and so we were able to achieve 50 ohm traces on the package itself. This gave us a smooth electrical environment up to the chip, and then we put 50 ohm terminating resistors on the chip itself. Now, each one of these can dissipate up to about 29 milliwatts. And because we have 202 of these inputs that are terminated on chip, it accounts for almost 6 watts. And this is more power than all but a couple of the chips at last year's Hot Chips. But for us, it's just a drop in the bucket. And what it does is it allows us to have very clean signals coming on chip. We can achieve rise times of ECL level signals of 150 picoseconds. Here's a slide of the processor organization. You can see we have a 5-stage pipeline, which is fairly shallow. The first pipe stage on the left there is instruction fetch. Then we go to registry read. ALU operations are in the next pipe stage in the middle. And then we read and write the data cache in the 4th pipe stage. And the 5th pipe stage, we write results back to the register file and also to the write buffer. And now, if you look, I won't describe all the connections in detail, but if we just look again at the instruction fetch pipe stage on the far left, I want to point out what we do in machine cycle. Basically, what we can do is send the program counter out from the data path to the instruction cache, go through the instruction cache RAM, read the tags out, do a tag comparison, check for parity on the data and tags. If there's a parity error, we convert that into a cache miss, and then we send a signal around the whole machine to stall in that same pipe stage. So that's quite a bit of work all in one 3 nanosecond cycle. And some other machines, like the R4000 for example, take 3 pipe stages to do the same amount of work. So if we pipeline the machine more heavily, we could run at a significantly faster clock cycle time. Okay, here's die photo, and you can see in the center area there's the data path. Going from right to left on the data path is the program counter, and then there's the integer execution unit, which has got the adder, barrel shifter, logical unit, stuff like that. The register file is in the center of the data path, and then because we support all the other MIPS ops other than the ones that I mentioned, we need to support load word, load byte, and store byte, and unaligned kind of references, load word left. So we have byte rotators, and then we have a write buffer. The instruction cache basically wraps around the data path on the side with the program counter, because that's what it needs to be close to. And then the data cache wraps around the data path on the other side, because then it's close to the write buffer, which it communicates with in the register file. Below the data path, you can see there's instruction decode and pipeline control, which is fairly small because it's a simple machine. And then flanking both sides of the data path, forming an H structure, is a H tree for the clocks. A few words about the caches. They both have the same organization. They're both 16 byte lines, and they have byte parity in their direct map. So it's a fairly simple organization, and the data cache is right through. What this allows us to do, the write-through data cache, is that in both the instruction and the data case, if there's a parity error, we convert it to a cache miss. And because we have no unique dirty data in the data cache, that means that we can get around any kind of parity errors in the chip, both hard and soft errors. And this is useful in bringing up the design when you have low yield initially. You don't have to rely on having the caches all work. Well, how did we achieve a 300 megahertz cycle time, which is, or clock frequency, which is higher than that of other CMOS microprocessors with only a 1 micron feature size? Well, one of the things that we did was we used custom ECL, and in comparison with custom CMOS, there are a number of advantages. If you think about the time to drive a wire, it's proportional to three things. First, it's proportional to the voltage swing of the wire, and it's also proportional to the capacitance. And then finally, it's inversely proportional to the drive capability of the technology. In custom ECL, what we do is we minimize the voltage swing on the circuits as much as we can. And because we have a custom layout, we also minimize the capacitances involved, just like CMOS custom designs. The bipolar devices have a very high drive capability, and so that helps the time driving the wire as well. To give you an example of some of the swings that we used on chip, basically the largest swing that we used other than the output drivers was a single-ended swing of just over a half a volt. And we used differential swings of a little under a quarter of a volt. And in some places we used cascode circuits, which I won't get into the circuit details, but basically that allowed us to use swings of between 30 and 70 millivolts. Now, since you can see the time to drive a wire is pretty much directly proportional to the voltage swing, by using voltage swings that are order of magnitude lower than those found in CMOS circuits, we can drive wires an order of magnitude faster. If you're going to keep the voltage swings very low in the millivolt range, hundreds of millivolts, you have to be very careful with your noise margins and basically count every millivolt source of noise. What you can see here is, on the left is a little schematic of an ECL gate. At the bottom there, the thing that says VCS and is connected to the lower supply, VE1, that forms a current source. And in all the ECL circuits, there's a current source to the bottom supply. This means that the current doesn't vary with time. This accounts for the higher power dissipation of ECL as compared to CMOS, which statically CMOS, if it's not running, doesn't consume any power, static CMOS. But it also means that we don't have any noise on the supplies due to switching that CMOS circuits would have. In a CMOS circuit, when a CMOS and say chip has its clock go high, it might see the supplies degrade by a volt due to the simultaneous switching of large numbers of circuits. But in ECL, we basically just draw the same current from the supplies all the time, independent of whether the circuit is switching or not. So that reduces a major source of noise right there. On the right-hand side, you can see lots of different noise terms, and I won't be describing all of them in detail. But I'll just be describing the one that's kind of most of the way down. It says delta VEE, 17 millivolts. That's basically the DC drop on our power supply network. We allowed 17 thousandths of a volt drop on the power supply network. So if you remember, we had supply current of 21 amps. And if our budget is only 17 millivolts, that's effective resistance of less than 1,000th of an ohm. How did we achieve that? Well, first we have gold bus bars that completely cover the die. And these gold bus bars are fairly thick. They're 25 microns thick. The normal top-level metallization is itself fairly thick. Aluminum, it's 2.4 microns. The gold is an order of magnitude thicker than that. And moreover, the gold has higher electrical conductivity than the aluminum. So we cover the entire die with the gold bus bars for the power supplies. And we dedicate the inner row of pads on the long side of the chip to power and ground. Finally, we bond the power connections to the package with extra thick gold bond wires to further reduce the resistance. The net result of that, well, first here is a die photo. You can see that it's very hard to see what's going on under the chip as compared to the previous picture, which was before we laid down the gold. In fact, for people who are working with the chips and have designed the chips, it even takes a little while to figure out which end of the chip is up. But I've made sure, and I've been careful here, that this is actually the right orientation of the slide. This shows the IR drops, DC IR drops that we were able to achieve on the power supply networks. I'll explain the color scale there. Red is basically the lowest drop, starting with 0 millivolts, and the dark blue is the worst drop, which is in this case a little less than 15 millivolts. So you can see that the IR drop, the DC IR drop on the chip is the least when you're at the bond pads, which is what you'd expect. And as you go towards the center of the chip, you get more and more of a IR drop. But still, it's not very much, only 15 millivolts. And you can see that the worst area is kind of in the center of the data path, where the adder is, and the adder dissipates a fair amount of power compared to some of the other circuits in the data path. So this is within our 17 millivolt noise margin. Okay. One of the other key things that we did was we used a phase lock loop to generate a high frequency on-chip clock from a lower frequency board clock. The board clock that we might see would be, say, 100 megahertz, and the chip clock would be 300 megahertz. We were able to generate any multiple of 1 to 8 times the board clock with the phase lock loop. And if you had, say, a 4-to-1 divider, that would mean that the board would only have to run at 75 megahertz. 3-to-1 divider would be, say, 100 megahertz. And what we did was all the I/O pads of the chip have flip-flops that are clocked with the board clock. And this means that no signals changing at the chip clock frequency cross the package into the board. So this reduces the design requirements for the board. Because we covered the die with 1 mil thick gold bus bars, it was very hard to see what was going on underneath the chip. But luckily in ECL, addition of scan capability is only a small overhead. ECL flip-flops are fairly large, and so it's only a small additional overhead. So all the on-chip flip-flops and all the boundary flip-flops clocked with the board clock all have scan capability, so that's boundary scan and interior scan. Okay. Now, I'll say a few words about the external interface. What we used in the external interface was large unidirectional buses. And we used unidirectional buses because you can achieve much higher bandwidth over unidirectional terminated transmission lines than you can with multi-driver buses. Okay. Also, we had a pipeline board cache. And the signals at the chip boundary basically could transition every board clock. And the board cache is pipelined into 2 or 3 pipe stages, depending on how you look at it. And the tags and the data in the board cache also are independently accessible, so we can pipeline the writes. I'll show an example of that later. If we did decide to run the interface to the chip at the chip clock frequency instead of the board clock frequency, we could have obtained a bandwidth of almost 5 gigabytes per second on the read side and 2.5 gigabytes per second on the write side. But if we run it at a 4-to-1 multiple, we are down to only 1.2 gigabytes per second on the read side and a little over half a gigabyte per second on the write side. The main limit that prevents us from running the board at that high clock frequency is that our cache is a 3-stage pipeline, and the middle stage of the pipeline is a RAM access, and that RAM access requires typically on the order of like 8 nanoseconds. Here's a block diagram of the external interface. In the center you can see the CPU chip, and I've drawn it with 2 concentric boxes. That denotes that there's an inner high-frequency chip environment with a chip clock, and then all the I/O signals only transition at the board clock. You see off to the right is the data area, which is both for instructions and data, and to the left is the tags. We have an 8-byte plus parity write path into the data area and a 16-byte read path. And you can see that we have flip-flops on just immediately before the data RAMs on the data side and on the tag side, and immediately after the RAMs as well. So there's a pipe stage or half pipe stage going to the cache, a pipe stage in the RAMs themselves, and a half pipe stage or pipe stage coming back from the external tag or data. The tag side looks pretty much like the data side, only we only need to write and read 11 bits, which is a tag amount. Here's an example of how the external interface can be used. What we see here is, imagine that we have 3 writes to different 8-byte addresses, so there's no merging in the on-chip write buffer. And imagine while those are in the process of being written outside the chip, we have an instruction cache miss. So in the first board cycle there, what we'll do is we'll send the probe for the first write out to the data cache, out to the board cache. And that takes a pipe stage. Then in the next cycle, the probe will go to the cache tags. And one cycle after that, the probe will be returning from the tags. Now, let me remind you that the reason why we need to do a probe here before we do a write is that the external cache is assumed to be right back, and the chip manages it. So we have to do a probe before we do the write to see whether we have a hit or not. Now, in the fourth cycle, the probe of the first data can be going through the on-chip control, which can be testing the returning tags to find out whether we have a hit or miss. Now, while this has been going on, following one cycle later is the second probe for the second write, and 2 cycles later, a third probe for a third write. Now, in board cycle 5, imagine that we have an instruction cache miss come along. It's a higher priority than writing entries out of the write buffer, and it will commandeer both the interface to the data side as well as to the tag side. So you can see that that progresses through the same pipeline, first going to the tags and then going to the data in parallel, going through both the tag RAM and the data RAM at the same time, and then going through the from, returning basically from both the tags and the data at the same time. Now this delays the beginning of the writes associated with those 3 probes by 1 cycle, but only 1 cycle after the instruction miss leaves the chip, then the writes can basically proceed. And so you see that we can have a lot of transactions going on at the same time because our external interface is pipelined so heavily, and then we also have the pipeline stores. One important aspect of the project were the CAD tools developed for the project, and I've broken them down into 2 main categories. First, we had tools that allowed us to synthesize the majority of the layout, and these were very important in allowing a small group of under 10 people to design the chip in a reasonable amount of time. We designed, as I said earlier, the CAD tools both for synthesis and analysis. Most of them were designed for the project. And they have another number of interesting aspects. First, the schematics that we used were actually graphical representations of C++ programs. And this allowed the full power and functionality of the C++ program language to be used in the schematics. So for example, we had, just a small example is we had for loops and if statements that we could embed with the schematics. Then these were translated into C++ code, and when the C++ code was executed, it would generate either the design layout or netlist or various other things. The design consisted of 554 different cells, of which only 93 were hand-drawn. The hand-drawn cells were typically the memories such as the RAMs and the register file, and a few circuits where density was very important, like the barrel shifter array cell. The vast majority of the cells, however, were designed automatically with the CAD system. So either layout of leaf cells was generated automatically, or these leaf cells were put together and routed automatically. The other phase of the design is analysis, and we did a number of things on the analysis that were somewhat novel. First, we developed, in conjunction with Stanford, a switch-level simulator, which allowed us to simulate the ECL circuits. And we used it to simulate the entire design, both at the behavioral level, there was behavioral capability, and also the extracted chip, including the caches. All 2/3 of a million devices were simulated before takeoff. We tuned the performance of the design with the bipolar switch-level timing analyzer that was also developed for the project. I've showed you on an earlier slide that we calculated the voltage drops on all the power supply networks. We also calculated the voltage drops on the ECL reference networks. And finally, all the other terms in the noise margin were checked, and also we checked to make sure that the bipolar transistors would never be in environments where they would saturate. Okay, so in conclusion, I think that the project has demonstrated that we can achieve a 300 megahertz operation with fairly non-aggressive feature size. And the logic density of the central data path is comparable to custom CMOS when using the same feature size. This should enable microprocessors to be designed in ECL that are similar in cost to CMOS microprocessors and not very expensive like large multi-chip module mainframes.